Oh, sure. Yeah.
So we can go. Second talk is by Kaizheng Wang, please.
Okay, thank you. It's my great pleasure to be here presenting my work on pseudo-labeling for covariate shift adaptation. So here's an outline of the talk. I will first introduce the basic setup of covariate shift adaptation and the key challenges. And then I introduce the methodology based on pseudo-labeling for model selection. And in the second half of the talk, we'll delve into the theory behind all of this method. The first comes a model selection theory for general result. And finally, we move toward the kernel regression and provide fine-grained adaptivity guarantees. So here's the basic setup of regression, just to make sure everyone's on the same page. We have a joint distribution Q of our feature and label. And we want to predict the label Y using the feature X. So for whatever function F, we measure its quality through this risk functional. That is just the mean squared error over my label, over my data population. Okay, so we want to find a good F to minimize the risk with the help of finitely many samples. So we get IID samples from the distribution. And then we want to construct an estimator, right? We want to find an estimator F hat so that the risk is small. And this is a generic form of the estimator. Just think of your Python function or R function. It's a function A, and it takes as input your label data set and some hyperparameter configuration. You know, for example, the penalties and some step sizes and architecture of your model, etc. So there's a collection of hyperparameters to choose from. Okay, that's a generic setup. And usually the dependence, the performance of your final model crucially depends on your choice of hyperparameter. So in practice, how would we do that? Well, the most commonly used approach is the holdout validation paradigm. I have my label data, but I don't use all of them for training. And instead, I start with a data split into training set and a validation set. So on the training set, I can run my favorite learning algorithm, regression algorithm, for a collection of hyperparameters, right? And on my validation set, which is held out from the training process, I've constructed a risk estimator, which is simply just the empirical risk. Okay, no, nothing fancy. And I'm going to use this empirical risk to evaluate the candidates and choose the final model. So that's a very basic holdout validation. And it works very well in practice, as long as you have sufficiently many label samples from the distribution, right? Both training and validation require sample from a distribution. Okay, so that is kind of the standard setup. But in practice, we often encounter an issue called covariate shift. We still have the same goal. We want to predict Y from X. That works well for one distribution. But the issue is the cost. So it's too costly to directly get label data from that distribution. So as a compromise, we get label data from a relevant distribution named P and some unlabeled data from Q. So we hope this unlabeled data still provides some useful information toward the final performance metric. So that's this is our setup, labeled data set and unlabeled. Okay, so there are lots of examples. So now everyone is talking about the chatbot and large language models. So imagine you want your language model to specialize in some domains like business negotiations, trying to convince the customers to buy your house, to buy your car. But your model could be pre-trained from a label data set, you know, from a very different domains like news articles, Wikipedia pages, etc. So there's a domain shift here, and also self-driving. So suppose you want to train a self-driving algorithm that works well for New York City. That would be super helpful for me. But your experiment or observation data come from Berkeley. So that's very severe shift. And the challenge of your covariate shift is ubiquitous. So how do we tackle that, and why is it challenging, right? So let's see. We'll surely see an example. And of course, there's nothing you can do without any assumption, because we don't observe any label here. So the standard assumption here is that the distribution shift only occurs on the feature level, and the conditional label distribution is preserved. Okay, we call the two distributions source and target. We want to use source data to facilitate learning in the target. Now let's see an example to illustrate the challenge. So we have this synthetic data. The X ranges from 0 to 1 and is mostly concentrated on the left. So the data is only sparsely distributed around the right. And my true functional relation is this cosine function, okay? So it's a very simple function relation, but the gray dots represent my data, okay? So how do I learn this function f star? Well, I can use kernel ridge regression with soft-leaf kernel or whatever other smooth kernel you like. So let me use kernel ridge regression, and there's a penalty parameter. I run kernel ridge regression with small, medium, and large penalties, and that results in 3 different curves. So small penalty, you get the red curve that is very wiggly because you have low bias and high variance. Whereas for the sine curve, you have large penalty and it's overly smooth. The blue curve seems to strike a balance between the two, right? So now my question is, which one is the best? You run your algorithm from your data, you get these 3 models, and of course you can try other lambdas to get more. How do you choose, right? So this is a very vague question. First, you need to make it clear, what do you mean by being the best? What's your performance metric? Because we all know beauty is in the eye of the beholder. So what is the beholder here? Then if you look at this figure, it depends on how you evaluate the function, okay? So if you, let's say, if you focus on the performance on the left from 0 to 0.5, then the blue one is the best. Okay, you can see that visually, or you can do some calculation. You can calculate this L2 loss. But if your performance metric is associated to the right half of the interval, so you care about the right, where you only have scarce data, then actually red one is the best instead of the blue one. The red one is under smooth and is too wiggly for the left, but it's just okay for the right. Okay, so there's no universally good model. And the best model, quote unquote best, certainly depends on your test distribution, where you want your model to generalize to. Okay, so you can try different test distributions and you will get different sorting, ranking results. Okay, so how do we use some unlabeled data to learn, to help better select a model for the target? That's a key challenge we want to tackle. Now, here's a method. In short, we want to do holdout validation with pseudo-labels because we don't have real labels on the target data. Now, so let's first make our life easier through this imaginary experiment. We have label data from the source, and we train a bunch of candidates. And we also have label data from the target. Then we can continue to use the holdout validation idea. Because we have label data from target, then I just evaluate those candidates using the empirical loss on the target, right? But this whole thing doesn't work because your target labels are missing. And that is the only bottleneck. Once you have the labels, you can run this process, you can implement it. So now in order to implement, let's just create the labels. That's a very direct resolution. So the idea is to fill the missing labels through imputation. So question. That's right. So it depends on how many samples you have. If you have very rich samples from a target, then you should certainly directly run ERM there. But if you have very limited sample from target and a rich sample from source, then You wouldn't just do ERM on target. You will combine the data. That's a good question. Yeah. So whereas in our extreme case, we don't have any label here. So now we want to implement the process. We need to fill the labels through an imputation model. So I use my data, my label data to train an imputation model and then generate the synthetic labels. And finally, I pretend these are the real labels and conduct risk evaluation and model selection. So at least you can implement it naively. And this idea is nothing new. In machine learning, it's called pseudo-labeling. And you can iteratively run this. You can further refine your imputation model and your pseudo-labels, and that will be related to this self-training. And they are very heavily used to reduce the labeling cost. And in classical statistics and causal inference in particular, you can, it relates to the idea of regression imputation for handling missing data. And of course, there are different approaches toward such challenge. For example, you can do reweighting or matching, but those are different from our focus. Okay, so we'll focus on the regression imputation idea. Now, so here's the method. I have labeled source data and unlabeled target data. Now, from the labeled source data, I train a bunch of candidate models like this illustration from under smooth to over smooth. And of course, you may have different hyperparameters. And on the other batch, I train an imputation model. My candidate models and imputation model are different. They are independently trained. Okay. And now I'm going to use my imputation model to create pseudo labels because my target data are unlabeled. And I just generate synthetic label, pretend they are the real ones. So that's going to be my risk estimator. You have a model, give it to me, and I will evaluate using my pseudo labels. Okay, so finally, I can use these pseudo labels to evaluate the model and choose the final one. Okay, so that's the whole pipeline. It's very easy to implement. The key is to run this holdout validation using pseudo labels or synthetic labels. So, but there seems to be a chicken and egg dilemma because on the one hand, we want to we don't know which lambda, which hyperparameter is the best to use. So we want to find some data-driven way to tune this lambda, right? We want to select a good lambda with the help of an imputation model F. But the imputation model itself requires another lambda tilde, right? So there seems to be a chicken and egg dilemma. To find a good lambda, I need a good lambda tilde. And so in order to make this run, we need to understand the interplay between those two, especially the quality of imputation label here. Okay, so now let's take a closer look at the imputation label through a model selection theory. Okay. So the whole idea is holdout validation with pseudo labels. Now let's look at this clean version of the problem. Let me treat my target data as deterministic, as fixed. You can condition on them. And I have n samples from the target that are deterministic, and I generate n pseudo labels. The labels are generated from a previously trained model. So those are random variables. You have n random variables. It's a random vector. And for simplicity, let's consider a normal case. They come from a normal distribution. And these are pseudo labels. I have candidate models. I'm going to just minimize my empirical risk with respect to the pseudo labels, right? The question is, how well does it work, right? My ultimate goal is to approximate a true function f star. So my performance metric here is the mean squared error toward the f star, not the pseudo labels, right? There's a discrepancy between my criterion and the real one. So you can imagine the error in the pseudo label will have some impact on your final performance, right? You don't want them to be too large. And the error comes from two sources. First, it may not be centered around the true target. And second, there's some randomness. So you need to analyze the impact of bias and the variance. And here we can prove an oracle inequality, showing that using this pseudo-label to select model, you get the excess risk of your final model is approximately the same as the minimum, the best in class, plus some overhead. And this overhead comes from two sources. First is the bias in your pseudo-labels, and the second one relates to the variance, right? Because my labels, my random vector of pseudo-label has some variance. Okay, so you can view this as a bias-variance decomposition, not of the mean squared error, but of the impact on model selection. So let's compare this to the traditional one we learned from all of the statistical learning classes. So this is the one we just derived. You have pseudo-labels and their bias has this impact. This is the impact of variance. But what about the traditional bias-variance trade-off? Well, for mean squared error, you have the same bias, but the variance has a different dependence on the covariance structure. For mean squared error, your variance will affect the final results through the trace of this whole thing. Whereas for the impact on model selection is much milder. It's just the operator norm here. So if you don't have too many models to select, then this overhead, the last term is much smaller than the trace term here. And as an illustrative example, in the holdout validation idea, if there's no pseudo-label but real labels, for holdout validation, I'm using noisy but real labels, then there's no bias, and the noise are uncorrelated, so the variance, the covariance matrix is just a sigma square identity. Then the operator norm and trace will differ by a factor of n. So this discrepancy tells you that the variance has the model selection doesn't depend too sensitively on the variance, and you can tolerate lots of variance. So the variance has a much weaker impact. You can use very noisy labels and still get a faithful model selection result. And that the practical impact, the practical implication of this observation is that for good pseudo-labels, you want them to have low bias and reasonable variance. So if you can generate pseudo-labels with low bias, then probably it will work. It will help you get a faithful evaluation and selection. So this part has nothing to do with particular function classes. It's quite general. And finally, let's move on to the model selection, to the kernel ridge regression and get fine-grained result. Okay. So this is in kernel ridge regression, this is how the model method works. Still the non-parametric regression example I showed before, you get lots of data. And I train an imputation model in this pink color. It's very wiggly, it's very undersmooth. Because according to the theoretical study, I need pseudo-labels to have low bias and reasonable variance to suppress the bias when you train, when you use kernel ridge regression, you would do undersmoothing. So this is my imputation model. You wouldn't want to use it directly because it has lots of noise. But you use them to label your target data and then perform model selection. It will give you much better result. So for model selection using the pseudo-labels, I can get this red curve. That's gonna be the final model I select. Whereas if I don't use this pseudo-labeling approach, I just totally ignore any target data, just use my label source data for both training and selection, I will get the blue curve. So since I focus on the performance on the right, where your source data is scarce, then you see this naive method will perform worse than the pseudo-labeling idea. So it's very interesting observation that the very noisy pseudo-labels, they are not good to use directly, but they're useful for model selection. So finally, let's delve into kernel ridge regression and derive the adaptivity guarantee. So this is the basic set of kernel ridge. Yeah, summary.
In both, so you have the operator norm log m over n. Is there a variance term from the?
Yes, this is, you should treat this as a variance term.
No, but the s is what s is the covariance of the. Oh, it's the covariance of the noise. Okay.
Yeah, you have n pseudo labels, so you have a and the noise here come from the randomness of your imputation model because it's pre-trained from another distribution. Okay, kernel ridge. So this is the basic set of kernel ridge regression. You just need to minimize a combination of empirical risk over your label data and a penalty term, right? And you search over a reproducing kernel Hilbert space, and we assume the realizability assumption that the true function belongs to the Hilbert space. Okay, and kernel ridge regression is nothing but linear ridge regression in a transform space, in the sense that once you have a kernel, you can find a Hilbert space and a feature mapping from your original domain to the Hilbert space, so that you're just running kernel regression after the feature transform. Okay. And this is how we implement our idea to kernel ridge. So I have labeled the source data. I do a splitting to train candidate models and imputation. So how do we choose those lambdas, right? So first of all, for the imputation model, we know we want to have low bias and high and reasonable variance. And having low bias means I choose a small lambda. And theoretically, you can choose 1 over your sample size. That's a small, reasonably small lambda. And for the candidate models, you want to look at different whole spectrum of smoothness, from very under-smooth model to over-smooth models. So you choose a geometrically increasing sequence from very small penalty to constant penalty. Okay. But the imputation model is based on an under-smooth model. And this is a one sentence summary of the main result. Our final model has the same performance as running kernel ridge regression on NE label samples from the target with optimal tuning. So this NE refers to the effective sample size. It measures how much information can be transferred from a source to target. We'll talk about that. And this whole result illustrates it highlights the adaptivity, because we can adapt to the structure of the target distribution, and we can also, implicitly select the optimal penalty through the label, so the pseudo labels. So more concretely, here's the excess risk bound. I'm interested in the target distribution, and this is the feature covariance matrix under the target distribution. And as in any study of kernel ridge regression, the spectrum of the target covariance matters a lot. So I find these are the eigenvalues. And 3 common scenarios. First, if my feature has finite rank or covariance has finite rank, then my excess risk bound is D over your effective sample size plus a small overhead. The 1 over NQ is the target sample size that is unlabeled. And if your spectrum, if you have infinite dimensional feature, the spectral, there's an exponential spectral decay, then you still have a very tight bound. So 1 over the effective sample size. And whereas if you have polynomial decay, like in most of the general non-parametric scenarios like splines or Sobolev space, then you have a non-parametric rate. So the final excess risk bound has 2 terms. First one is your the first one is your effective sample size. It's a function of our effective sample size. The second term is the function of your target sample size. That is unlabeled. And the first term is not just a function of effective sample size, but it's actually the optimal rate if you have any label samples from the queue, which we don't, but it adapts to the structure. And second term is very minor. So you don't need too many unlabeled data from the queue to make this term small. So what is the effective sample size here? And this is our definition. I have NP samples from the source. And the effective sample size is defined through this relation. The largest T so that a multiple of my target covariance is dominated by the right-hand side. This is the source sample size, source covariance, and plus an additive term. So where does it rise? Well, you do some calculation because kernel ridge regression has analytical form solution. So you can do some algebra and see that the following two terms are essentially the same. You can run kernel ridge regression, optimal kernel ridge regression using NP labeled source samples, or you run kernel ridge regression, use this number of labeled target samples. In both cases, you choose the optimal tuning, then you will get the same excess risk bound. So it's that's where this effective sample size originates from. And beyond that, we need to show the pseudo-labeling helps select a near optimal lambda like that. So that the second part, the model selection part, is done through the general result I just presented. And finally, let's look at some examples. So just to illustrate the adaptivity, the first example is very commonly used. I assume the target data has a bounded density, bounded likelihood ratio with respect to the source. So the likelihood ratio is bounded by a number B. And if this is the case, then immediately we see the target covariance matrix is bounded by B times the source covariance matrix. You can immediately get it from the likelihood bound. And if this is the case, you look at the effective sample size, you get a lower bound. The effective sample size is at least the source sample size over this ratio B. So if P and Q, yeah, question?
It might be the case even for two Gaussians with different.
Perfect question. Yes, that's right. We'll come into that. Yeah. So in general, you will need for two Gaussians, you wouldn't have this bounded density ratio, but you can still have a dominance between their covariance. And then from here, you can still get a lower bound on effective sample size. That's right.
So the covariance here is the covariance of the original data or the covariance at are we in kernel ridge regression?
Yeah, the transform feature in the Hilbert space.
Okay, so these are the covariance operators.
Yes.
Okay.
Yes.
And you're handling the infinite dimensional case.
That's right. That's right. So
you're localizing at like a radius of like 1/NP, right? In Q norm, though.
That's right.
Why is that the right radius?
Like here?
Yeah, so because you're looking at essentially you require this inequality to hold on functions that do not have small enough Q norm, right?
That's right.
So why is the critical level 1/NP in the Q norm? That's a bit kind of interesting.
Yeah, so that's a good question. So for kernel ridge regression, it turns out 1/NP is the smallest penalty level, so that you can still have a covariance concentration. Yes.
Okay, so it's just to have the like for Bernstein to go through.
No, that's right. That's right. Okay. So for this case, you can treat the ratio B as a conversion ratio. There's a discount of your label sample by a factor of B, and you use our result, you can get an optimal excess risk bound. And more interestingly, our f hat adapts to the unknown b because our algorithm doesn't know any b or any eigendecay, but it automatically adapts to that. And the excess risk bound from our theorem in this case will match the lower bound in the paper by Rees and Tong Ma and Martin. Okay, so they established a nice lower bound here. Okay, so more interestingly, let's look at a case where the absolute continuity doesn't hold. This is the extreme case. My source data, my source distribution is spread out. It's uniform between 0 and 1. It's uniform distribution. And my target data is only at 1 point.
The kernel space after embedding, or what?
In the feature space, in the original feature space. Yeah.
But then you go to uniform distribution. There is no such thing in the space.
That's right. So here it's just a original space. Yes, the original feature is finite dimension, is one-dimensional, but we consider non-parametric kernel. So this is an example. I have my source data is spread out over the domain, but I only care about the performance at 1 point. So in conditional treatment effect estimation, this is commonly the case, right? And I have non-parametric functions. So what is the effective sample size in this case? If I have n samples from a uniform distribution, you're sure none of them will lie at this point exactly. There's no, because of the singularity, right? Then how much information can be transferred? So clearly this cannot be a linear multiple. This cannot be a proportional transform, right? Due to this non-parametric effect. And through the calculation of this bound, because for this case, you can explicitly calculate the spectrum of all these operators. And it turns out the effective sample size is the square root of your source. So it's not proportional, right? Marginally, as your sample size gets larger and larger, the conversion ratio decreases to 0. And from this result, you can get a non-parametric slow rate of the excess risk, which still turns out to be optimal. So the pseudo-labeling approach can adapt to this singular case. And in this example, we can also show the necessity of adaptation, because for every individual model is either suboptimal for the source or suboptimal for the target. So if you don't know which is going to be your target or test distribution, you cannot choose a good model. You have to adapt to adapt to the target, you need to use some information from that distribution. Okay, so here's a summary that we tackled the problem of covariate adaptation given unlabeled target data through the method of pseudo-labeling. And in the theory part, we first derive a general result for model selection. The general requirement on pseudo-label is to have low bias and reasonable variance. And that's kind of the practical guidance. And finally, in the kernel ridge regression example, we can derive adaptivity results. The paper is available on arXiv and also on GitHub. So I'm happy to address the questions.
Great talk. Questions? Yeah, Samery.
Something in terms of the effective sample size plus 1 over n cube. Do you think there is a possibility to have a rate that is like the minimum of those two terms, or that integrates the two terms? So it's almost feels, do you see why I'm asking this? Yeah. It almost feels like we're losing a little bit of the information.
No, that's right. I think this dependence is optimal in our case because you don't have any label in the target. Yeah. That's right. So the target data always give you some overhead.
Area where maybe you could do a bit more than this?
I think so. If your target data is labeled, then I believe you can prove the minimum, okay, like the work by yourself. But if your target data is unlabeled, the issue is that in order to, because our performance metric is the out of sample error in the target distribution, that's population risk. So you only have unlabeled data, finitely many samples from there, there's already an approximation error.
Maybe I also would like to ask something. So,
Sure.
so I'm from the non-parametric statistics community, and so if I see just this example that you have, that on one side you have a lot of covariates, and on the other side very little, then what we would do is we would say, okay, let's do some local smoothing, kernel smoothing, or so, and choose an adaptive bandwidth, and that can basically deal with that, and it gives you optimality, and you don't need any additional data, unlabeled data, because there's no information about the F, so it doesn't give you anything about any additional knowledge about the regression function that you want to recover, so you don't need that. So why not doing that? Why do you want a global approach, which is kernel with regression and a fixed number?
Yeah, the perfect question. So and the answer is already in your question. So you talk about the comparison between local approach and global approach. So if you are doing non-parametric regression in a local with local smoothing, that's a holder class or Lipschitz class, then the method you just mentioned would be optimal. You don't really need label data or unlabeled data from target. You can directly do an adaptive smoothing. But if you are looking at soft-lift space, where the smoothness is a global metric, let's say it's a global integral of the derivative, etc. So the regularity is global, and then you will need the global structure. Yeah, it's like in linear regression, because of this the global constraint, the functions are more rigid than the holder functions. Yeah, so even if some points are far away from you, you may still do it.
So I could always sample more unlabeled points, right? And could add them to my sample, and would that make that the whole procedure then better or not?
You mean unlabeled data?
Yeah, unlabeled data from a third distribution, which you choose as a statistician.
Yeah, that's a good question. But you don't have labels, right?
But then you still do the same approach. But that feels like that you can always improve also in terms of the 1/NQ or so. Because if you get more and more information about.
Okay, so but so this okay, so this NQ is the number of target data.
Right.
Yeah, but if you draw samples from the source, not the target, so now that means you augment my existing setup with more source label, with more source samples.
With another distribution.
Yeah, another distribution. Then I think there will be another term. Yeah, it's not directly because you're not directly drawing sample from the target.
But Kaizheng, your error metric here is L2Q, right?
Yes.
So why is it useful to have so the approach that you had suggested is I sample covariates from another source, right? Why does that help me adapt to the L2Q metric? Right?
I think it helps to consider this example. So my source is uniform between 0 and 1, and my target is just 1 point, let's say at 0.5. I only want to evaluate my function at 0.5. Now I keep drawing samples from the source, unlabeled sample, but that probably wouldn't help.
More question? Yeah. Thanks again. Great talk.
Thanks again to everybody who presented today. Just a quick announcement. We have a reception plus poster session upstairs on the second floor, starting now, essentially. So we can relax around. I don't know if there is wine and beer, but I did order, but we'll see. Oh, 1 second, people.